Thank you for the kind introduction and for putting together such an interesting workshop. I'm very happy to be here, and it's a great pleasure to be invited to speak. So what I want to talk about today is a joint project with Anna Dall'Acqua, Marius Müller, and Manuel Schlierf from Ulm and Augsburg, respectively. And I'm going to use the blackboard, but I'm aware that my handwriting might not be the best. So if you want me to rewrite something which is not legible, please let me know. Too small. So let me explain what I mean by this problem. So total curvature I will be talking about today is the so-called Willmore energy. And what we look at is maps F from a two-dimensional smooth surface into Euclidean space. Every map I write here, every curve will be smooth, okay, for the analysts. Yes. And okay, sigma here is two-dimensional, of course, and a closed surface. It doesn't need to be orientable, but closed means without boundary and compact in this. And for such an immersion, Willmore energy given by a normalizing constant, and then we integrate over sigma, and we take h squared d mu, okay? The Willmore energy. Okay, of course, we integrate over sigma here. This is clear, and h is the mean curvature that we've seen also before in the mini course by Blanche. It's mean curvature vector. Okay, let me emphasize that for n equals 3, this is the sum. H is the sum of the principal curvatures times a local unit normal field. This is the mean curvature vector, and so there's no dividing by 2. This is why I put the 1/4 here. Okay. And what is mu here? Mu is the volume, two-dimensional volume measure or area measure induced by the metric, and G is the metric which we get by pullback under F of the Euclidean metric in Rn, making this an isometric immersion, if you want. Really, we only look at things which are in Rn. You can think of dysfunctional acting on submanifolds, but it is important in this context to allow for points of multiplicity, which is why I only assume immersion here. So in particular, the image of such an F would have like this is a concept of total curvature for immersions of surfaces. Maybe a side note, if we have a curve in, say, Rn, then usually there's no ambiguity to say that the total curvature is integrating over the curvature ds. This appears in many classical theorems like Fenfeld's inequality or the Farey-Milnor theorem, and is related with many topological and geometric properties of curves. And here in 2 dimensions, it's maybe not immediate what one should choose, but we make the choice of taking the mean curvature here in the Willmore energy as a concept of total curvature for surfaces. Yes, please.
Square in your definition of the Willmore, but you have no square for curves. Is this?
Yes, and this is on purpose. Thank you. Because we are in 1 dimension here, this is invariant with respect to dilations. And we will see that this is also invariant with respect to dilations. Okay? And this is a property that we want because, well, rescaling in space does not really change much, right? Okay, you can do the n-dimensional Willmore energy by putting the dimension here if you want to get the same scaling type behavior, but 2 dimensions is very special. Okay. I should also mention, because we have been having a wonderful lecture about varifolds, that you may also define this for 2-dimensional varifolds. If the mean curvature is square integrable, and you can also do calculus of variations on varifolds for this energy, but this will not be the purpose of this talk. Okay, so just smoothly manage. Okay, the most important property for this functional is its invariance. Okay, and we write it like this. So if we compose from the left with certain maps phi, the energy will not change. I've already said that here we do include dilations. Okay, so if we dilate the surface, the mean curvature will scale like 1 over the factor. The area element will scale like vector squared, so this is cancelling. We have this invariance. Of course, we also have invariance with respect to isometries. But what is really the striking point here is that we may also take a particular map, which is the inversion in a sphere of radius 1. We don't quite get the full invariance here, but then we get that the Willmore energy of the inverted surface is the Willmore energy of the original minus 4 pi times the multiplicity of f at the origin. Okay. This is why I'm including this in invariance, because of course if the surface does not touch the origin, we can do the inversion and the energy will not change. But this is also understood in the case where we have a point where 0 lies in the image of our immersion, then we get this multiplicity result, which is really a key identity to derive many properties from this energy. Okay, so we have invariance with respect to dilations, isometries, and this map. These generate a group, the Möbius group of Rn, and this means that this functional is invariant with respect to conformal transformations of the ambient space. Well, as long as we don't invert in points which lie on the surface. And this is beautiful, but it's also very nasty from the analytic point of view. Normal invariance. Because the group, the invariance group of this energy functional is non-compact, and this is generically bad for calculus of variations, PDEs, passing to limits in critical points, etc. So this is a very inconvenient property from the analysis. Okay, let's deduce 2 important properties from this boxed identity here. The first one is if we just estimate this to be non-negative, we easily get that we translate the surface such that it includes 0, and we easily get that Willmore energy is bigger than 4 pi, and one can in fact show that one has, with equality, if and only if f is defined on the topological sphere and parameterizes the nicest way possible the round sphere. So round spheres are the absolute minimizers of the functional. Of course, because sigma is closed, this can never vanish identically. There's no closed minimal surfaces, but there is a, well, non-trivial, if you like, infimum given by 4 pi, and it's attained exactly by round spheres. Second important property we get from this here is a control over multiplicity. And this is the following form. So if Willmore energy is less than 8 pi, 2 times the minimum of the energy attained at round spheres, then F is injective, or equivalently in this case, it's an embedding. So really we have an embedded surface then in Rn. Liao inequality, and it's really a key property here, and in many of the papers containing results about Willmore, you will always re-encounter this threshold which guarantees that there is no points of higher multiplicity, which of course exclude some sorts of singularities appearing in minimization, gradient flows, etc. The last thing I want to mention here is, of course, the Willmore conjecture, which is about minimizer among tori. So if sigma is torus, then the Willmore energy of any immersion is bigger than 2 pi squared. Yes, and here we have possibility to get equality for the so-called cliff or torus, a round torus of revolution where the radii have a specific ratio of square root of 2. Yes, this is still open in general, but it's a theorem now in codimension 1. So, 2000. Okay, but in codimension higher than 1, it's still a conjecture. This is what I wanted to quickly give you about the second line of this title. Let's talk a bit about conformal constraints now. So let me give you a quick recap of the, let's say, conformal geometry of surfaces. Okay. For this purpose, I take sigma now to be a Riemann surface, so oriented, genus P, bigger than 1. Also allow for P equals 0 for the moment. And then we have an equivalence relation on metrics. We say two metrics are conformally equivalent if and only if one metric is a positive factor times the other one. U is a scalar smooth function. And yeah, we usually write it by e to the 2u, but okay, it's just a positive function times the other metric. And the cosets here are called the conformal class of the metric. And in view of its invariance with respect to these conformal transformations of the ambient space, it's a natural setup to study the minimization of the Willmore functional in a fixed conformal class. And this is the minimization problem I want to talk about today. We want to minimize for a fixed sigma and a fixed conformal class. We want to minimize Willmore energy among all immersions with well, metric under pullback. Here, given n, of course, sigma, and a metric G0. This is a minimization problem one can study, and in fact, it's quite related to the Willmore conjecture, and understanding of this minimization problem may be very useful for in the context of trying to extend the Marquez-Neves result to the higher codimension case. There is an existence result already of a smooth minimizer. If the, well, not so surprising maybe, the infimum is less than 8 pi. So if the surface and this given reference metric G0 admit an immersion with energy less than 8 pi, then we can run the direct method. Okay, you have to do quite some work to do that, but you can run the direct method, and because of the Liao threshold, there's nothing going wrong, more or less. No points of multiplicity, no singularities. In this case, this is due to Schätzle, 2013, and also yeah. This constraint is quite inconvenient analytically, so let me quickly give you some comments about the structure constraint. Bigger than 1. Otherwise, if the genus is 0, then there's only one conformal class on the sphere. But in this case, well, what we would like to do to implement this analytically is to find like a canonical representative of a conformal class. One way to do so is with Poincaré uniformization. Giving us a unique called Poincaré metric in the equivalence class of any G. So this is right M point for the Poincaré metrics. So these are metrics of constant curvature. And unit volumes. This is canonical representative in each conformal class, but okay, there's another invariance we of course have to take into account. Of course, the Willmore energy will also not change because, well, all the objects are geometric. It will not change if I compose now from the right with the diffeomorphism. Okay. So in some context, if the energy is here invariant with respect to this, we should also incorporate the constraint in a way which takes this into account. So we naturally want to mod out in this space of Poincaré metrics by the action of diffeomorphism. So one way to do that is to look at the so-called moduli space. Diffeo. Okay. If I mod out by diffeomorphisms, then I get the modular space, which is not so nice in terms of its structural properties. It's generically not a manifold. Another way to do that is to mod out instead by only diffeomorphisms which are homotopic to the identity. This gives me Eichmüller space, which now is a manifold, but there is again an issue here because from the analysis point of view, because if I take the map, if I want to use the Teichmüller space to represent the conformal class, I have the problem that the map here, I think. I would like to have look at the map which associates to any immersion the representative given by the Poincare metric in the Teichmüller space. Okay. This is a smooth map, but not a submersion. So it's not that helpful to understand the analytical structure of this constraint. It's not a submersion at isothermal immersions, which includes DMC immersions or surfaces of revolution. Okay, so again, this is bad news because, of course, if we could write the constraint set as a a level set of a submersion, this would give it a nice manifold structure, and we can use a method of Lagrange multipliers, for instance, to get an equation for minimizers or critical points. So this was just to tell you it's analytically inconvenient. Constant mean curvature, sorry. Constant mean curvature. Yes. So the minimization problem already has an answer, a partial answer, but it requires this assumption that the infimum is less than 8 pi. And of course, we would like to get around this. And what we did in this work is we looked at a dynamic approach to minimization via gradient flow. And we will see that this gives partially at least a way to get around the 8 pi. Let's talk about the Willmore flow in the absence of a constraint. So general idea of a gradient flow, minimize by deepest descent. Okay, so you can think of the following picture. We have an energy landscape, W. We start with some initial datum of gradient descent, and at each time we go down in the direction of the negative gradient, the direction of steepest descent, okay? And we hope we find something useful in the limit. Of course, we cannot expect to get to the global minimum here, as I was already drawing this picture. We can also stop at a local minimum or a saddle point. In the case of the Willmore flow, this Willmore energy, this leads to a PDE. So a family of immersions now, and time interval 0t, all defined on a common surface sigma, is a Willmore flow. If velocity negative gradient of the Willmore energy, okay, whatever that is, you can write it down, you can compute it explicitly. This is the Laplace Beltrami of the mean curvature as the leading order term. Then we have some quadratic term in the trace-free part of the second fundamental form here, multiplied again with the mean curvature. This is a PDE now. So if there was no quadratic term and no Laplace, this would just be, and no minus, then this would just be a mean curvature flow. But this is like a higher order version of mean curvature flow, if you like, because we have an additional Laplacian here. So it's a fourth order geometric flow. Q of A0, so A0 is the the second fundamental form, and then we subtract the trace, yes. Trace-free part of the second fundamental form. Sorry? Yeah, okay, let me say in codimension 1, Q of A0 H is just the length of the trace-free part times H. In higher codimension, it's some form of contraction of A0 and H, which is bilinear in A0. So it's a cubical term. This is from the PDE perspective, this is the important thing. It's cubical, so it's very, very bad because the energy is only controlling the quadratic. Okay, so this is a quasi-linear fourth-order geometric flow. In particular, I like to emphasize that there's no way to use maximum principles, at least no way that we know of, for this flow. And yeah, it's quasi-linear, so we don't know if the flow exists globally. We don't know if it converges. And in particular, it's not clear if it actually will give us a critical point in infinite time, as we hope, because we don't know if it exists. There is, however, some work on the Willmore flow already. Again, mention Kubert and Schätzle in their paper from 2004, which gives that if we have an initial datum from the sphere in R3 with Willmore energy less than 8 pi, then we have global existence and convergence. The limit is around sphere, actually. Okay. Again, I from the Liao inequality to rule out points of higher multiplicity and thus singularities. It's also optimal. There was this example studied 5 years later by Simon Blatt. We have following initial datum, surface of revolution, profile curve is like so, revolving around the x-axis. This is an immersion of a topological sphere. But the winding number, which is encoded in this initial datum, does not allow the flow to converge. This develops a singularity. And if you look at this closely, you think that the loop gets very, very small and approaches the axis. You would see two spheres, right? So this has energy 8 pi plus epsilon. So we can find it for any epsilon. We can take the initial datum to be order 8 pi plus epsilon. So above this threshold, and this initial datum necessarily leads to a singularity. So this threshold here is optimal. Okay. However, still up to date, we don't know if this happens in finite or infinite time, by the way. Open problem. Okay, so this was about the classical Willmore flow. I want to get back to the minimization problem in the box here and talk about tori now. Sigma is torus. And in this case, we have a good way to understand the conformal class. So if we have a map immersion of the torus into Rn, recall that this is equipped with the pullback metric now, then we find conformal diffeomorphism from complex plane mod E plus omega z or some complex number for some complex number where we can take the real part between 0 and 1/2 and bigger than 1. This is a theorem that equipped with the pullback metric here, and here we take the flat metric. There exists a conformal diffeomorphism, and the omega here is unique if we take this restriction. So let me visualize the admissible omegas here. Unit circle here. We have the strip 1/2, and then the admissible set, okay. Omega in this set, which I will denote now. Yes, and because of the omega being unique, we can understand the conformal class just as this number, this complex number omega. I write in slight abuse of notation, I write C of f, which is really C of the conformal class of the induced metric by f, defined as omega for the conformal class. Okay, and now with realizing this constraint, we can at least formally define in quotation marks conformally constrained Willmore flow. Well, what we want to do is we want to go into the direction of steepest descent, but only the one which is allowed by preserving the conformal class. So what we would do, okay, we would take the usual Willmore gradient, and we would like to project this onto a suitable space. I write this P to the C of F now, and okay, this is a L2 orthogonal projection onto the space of infinitesimal conformal variations. This is a formal way to write down this equation. Actually, if we have a good way to realize the conformal class, we could also do this in higher genus, but I want to show you now that in the torus case, this can be done rigorously, and a priori we can just write this down, but of course we don't really know what this is, this projection here. We can take the space, okay, we have to close it. Close it in L2 so we can project onto it, right? Then we can compute this projection, but a priori we can write down this equation. We may not be able to write it down explicitly, okay? But then the disadvantage is that we don't know that the conformal class is actually preserved by this velocity. Energy will go down if we have a smooth evolution. This is not so difficult to see, but we don't know that the constraint is preserved. So what's the point of doing this in the first place? Sorry, what do you mean?
I mean the constraints. It's a submanifold, and you make the gradient perpendicular also to the constraints, like Lagrange multipliers.
Yes. This is actually what we will end up with in the end. Yeah. And of course, here the problem here comes is that we cannot realize trivially this constraint as a level set, because if it was a level set of another functional, which is a submersion, then there's the method of Lagrange multipliers, which allows us in a sense to write this down. But in general, it's not so clear how to do that, but we will see now an example where this can be done. And the theory is very rigorous. So let's talk about how rotational symmetry helps in this context. And what we look at now is we look at a curve, closed curve, with values in the upper half plane. At this point, this is just the upper half plane. We will get the hyperbolic metric there soon. And then we get a induced torus of revolution. Here's again the picture. We take the curve gamma. This may be a curve not embedded, okay? So this may be a figure 8 curve a priori. We revolve it around the axis, and what we get is a immersed torus in R3. And the important observations are the following, and this is why I write H2 here, because the Willmore energy is related with hyperbolic geometry of this curve now. The Willmore energy of this torus of revolution. I think this goes back to the work of Langer and Singer before, saying that the Willmore energy of the torus of revolution is a factor pi over 2 times another functional of the curve, E of gamma, the so-called Euler-Bernoulli energy of this curve. So this is now the quadratic version of the total curvature for curves. And here I write G now, okay. And G is the hyperbolic metric. Okay. So I look at the curve with my hyperbolic eyes. I look at the curvature vector. I take its hyperbolic curvature vector. I take its hyperbolic length. I integrate with respect to hyperbolic arc length. And then we have this beautiful relation of the energies. Elastic energy. And fortunately, a similar reduction by this symmetry can also be done for the constraint. Very good, otherwise it would not help that much. But the conformal class of a torus of revolution, it's well known that the conformal class for a torus of revolution is rectangular. So in particular, it will only move here along the imaginary axis. And we can actually compute the real number, which represents the conformal class now. This is the maximum of 2 pi divided by the length, and the length divided by 2 pi. Okay. And here, the length is the hyperbolic length. The hyperbolic length of the profile curve corresponds to the conformal class. And in particular, so the set of tori of revolution, V, torus revolution, with a fixed conformal class, which, as I said, is an imaginary, purely imaginary number, so I write it like I times y. This corresponds to a specific collection of curves in the hyperbolic space, hyperbolic half space, where the length is 2 pi y or is 2 pi. We have the class of tori of revolution with this conformal constraint, so the admissible class of the minimization problem. We have reduced the dimension now by the rotational symmetry, of course, instead to study curves where the length is either this number or this number. Okay. And of course, length fixed, this is like a much nicer constraint than fixed conformal class, but for this reduced complexity due to rotational symmetry, of course, it's equivalent. And let me also remark, rotational symmetry, you may think, okay, but then if we study the PDE, it's a PDE, still a PDE, okay, parabolic, but in one space variable, so Sobolev embedding is much stronger, so we can hope that everything is nicely, right? But really the singularity of Willmore is not due to Sobolev embedding, as you can see here. This is also rotationally symmetric, nevertheless we have the singularity occurring. This is the one remark to say that rotational symmetry helps, but it's not trivial that it helps, I would say. And the other thing is, of course, that I discussed the constraint before. The Teichmüller projection is exactly not a submersion if we are a torus of revolution. So there's another, well, let's call it again, analytical inconvenience, despite we reduce the dimension. We comment on the length constraint maybe down here now. So of course, now we have this set to minimize on or to study the gradient flow on. And as I said already, okay, we just have a real valued constraint now. And the key observation now is if we compute the first variation of the length at a curve acting on some vector field, this is the well-known formula that this is the minus the hyperbolic curvature tested against phi integrated here. If there was no g, this would just be the first variation formula we saw in Blau's talk for curves. So first variation of one-dimensional area, which is the length, is minus the curvature. Okay. In this case, we have the hyperbolic quantities. Nevertheless, this is not identically zero because for a closed curve in hyperbolic space, the total the curvature cannot be identically zero. There are no closed geodesics in hyperbolic space. This is really a submersion. This is, of course, the key point to. We are almost there now to state the full theorem, but so far we've only talked static. So we have established connection between the energies and the constraint. We have not yet established the relationship between the gradient flows. Because of course, in the static minimization, we could just minimize elastic energy with fixed hyperbolic length now. But this is not what the Willmore flow would do, as we see now. Here's the lemma. A family of surfaces of revolution, F gamma, evolves by conformally constrained Willmore flow. So this is the equation on the left. If and only if the family of curves satisfy the following evolution law. So this is what we would expect, maybe. Okay, this is what we would maybe expect from the static minimization. Minimize the energy, the constraint of fixed length, method of Lagrange multipliers. We get a scalar Lagrange multiplier lambda here, depending on gamma, which realizes the orthogonal projection here on the right. This is not the full story. We have a factor here, which is 1/4, and then the second component of the curve to the 4. Second component is the distance to the rotation. This is really the equation we get, and if we want to write this out more explicitly, let me give you the formula for this gradient of the elastic energy. This is the gradient of the elastic energy. Here we have the hyperbolic curvature, and this is, well, it's just a second order derivative operator. The Levi-Civita connection along the normal bundle of the curve twice applied to the curvature vector. So it's a second order derivative of the curvature. It's again a fourth order PDE. This we cannot reduce. Yes, this is the relation between the two. And of course, maybe the surprising part here is this factor, right? Telling us that the flows move in the same direction, if you want, but with a different weight. This is not only time, but also space dependent. So one has to be careful with this interpretation. So one can check that the length is actually preserved now, but due to this factor, it's a weighted L2 gradient flow. And of course, this factor needs to be controlled along the evolution. Okay. Let me finally state the theorem we have. Which will be on arXiv soon, I hope. So if we have a torus of revolution, and we take maximal evolution by the conformally constrained Willmore flow, formally constrained Willmore flow, then we have at least one of the following. Is A, as the time approaches its maximal existence time, the total scalar hyperbolic curvature goes to 0 along a subsequence. And if this does not occur, we necessarily have infinite existence time and convergence to a conformally constrained torus. Okay, so if there exists singularity, necessarily we are in case A. This would be not so interesting if we cannot exclude case A, but we can. Under the following assumptions, A cannot occur if, this maybe comes to no surprise, the initial datum has energy less than 8 pi, retrieving the usual condition to rule out singularities. What is maybe more interesting is the second one. If the length of the initial profile curve is less than 2 pi times m, this is the winding number. So if either of these conditions is satisfied, then we cannot have case A. So necessarily we have global existence and convergence and find a critical point in the limit. And in particular, this condition does not involve any energy control of the initial datum. We can find initial data with arbitrary high Willmore energy, which still satisfy this condition. The 8 pi can be removed in this context. Not completely, we have a substitute, but it's energy independent, or at least Willmore energy independent. There's still the length and the winding number involved. Yes.
In the winding number of the
feedback
field.
This is winding number 0.
Really the winding number.
Yes. So the if you want, is the Euclidean total curvature of the curve. Okay, that's one way to define it. And of course, if the flow exists, then this inequality is preserved. The length is preserved because this is the conformal class, and the winding number is also preserved because it's harmonically invariant. Okay. Last side remark, maybe as an application, you can find the existence of a new class of conformally constrained Willmore tori with revolution symmetry, of course. We can do this in R3 or in S3 because of conformal invariance and stereographic projection. They have Willmore energy bigger than 8 pi. In particular, they cannot be treated with the classical existence or the older existence result on conformally constrained Willmore minimizers. Of course, we don't know if these are minimal. We just know that they're critical. Well, they're not maximal. They have one. We have one direction where the energy goes up from this limit. Okay. Yes, I think that's all I wanted to say. Thank you.